here the shape of a drum. So it belongs to this kind of inverse problems. Namely, it's not only for billiards and domains, but you imagine you have a class of objects in which you have some dynamics inside, and you associate to them a certain set of data. Okay, so let's say you can call it spectrum. In our case, it will be a spectrum. So if you go to hospital, you do echography or X-rays, then you have all the the machine gather the rays which go through the matter, and then she tries to reconstitute the objects from that. So the question is, can one recover our objects knowing only a spectrum? This is an inverse problem. Okay. Today I'm going to present you two. Mostly one is important inverse problem related to billiard, but which is kind of connected to another one, the one of cats. The one of cats is the following. You take a domain, in our case omega, in the plane, okay, and you suppose that it is strictly convex, and the boundary is sufficiently small. Okay. Then you can imagine actually that it is the shape of a drum that sounds in different ways when it vibrates, and this vibration are called the modes of this drum, and you can try to understand if the way it sounds, if you hear the way it sounds, you can recover the shape when you don't see it. This is the question of the cats. Can one hear the shape of the drum? And it was in the 60s. Okay. And more precisely, you study the eigenvalues of the Laplace spectrum with Dirichlet boundary condition, for example. So you look for all the lambdas such that this problem has non-trivial solutions. Okay? And this you call it, all the lambdas satisfying that, you put them in a set which is the Laplace spectrum of omega, which is defined as the collection. They are actually strictly positive in that situation. The collection of solutions of eigenvalues. Okay, so this is the Laplace spectrum, and the question of cats can be reformulated. If I have my domain, if I have omega, and that I associate the Laplace spectrum, its Laplace spectrum, is this mapping J? Okay. When I put it this way, no, it is not injective because you can translate your domain. So we have to see things up to isometries. That's the question. Actually, this is related. So this spectrum gives the vibration modes of this of the domains. I'm not really a specialist of that, but it is related actually to propagations of wave, basically, stationary structure of the domain. So is it injective? So this is the first inverse problem. Actually, the answer is no. Okay, for convex domain, we don't know, but in general, if the domain is not convex, the answer is no, and the will explain later. There is another problem, which seems a bit unrelated to that. It's connected to, you can define it in terms of billiards. So we take again same condition, a domain with in the plane with strictly smooth boundary, strictly convex. You can play billiard inside of it. Namely, you imagine it is a cavity bounded by perfectly reflecting mirrors. And then inside of it, you emit a ray of light, and then it will bounce off the boundary according to the law of reflection that we know, angle of incidence is angle of reflection, and then it continues its trajectory. associate, again, the domain, it's periodic coordinates. Periodic coordinates is something that we understand quite easily. These are trajectories which repeat themselves after a finite number of times. Here, for example, a periodic trajectory of period 4. And also you can notice that it turns once around the boundary. Imagine, for example, a trajectory which do many turns. Let's try to do something satanic. Okay, so something like that. So you turn twice, 2 turns, and 5 bounces. So 5 period. This you call a periodic coordinates, and you can look, when you have a periodic coordinate, you can look at the perimeter of this periodic coordinate in terms of length. So, and this defines the length spectrum. It's not lab, it's L of omega, the length spectrum. It's the collection of perimeters of periodic coordinates. Okay, and for some reasons you need to consider the closure. Namely, when you increase the number of bounces, you will have periodic coordinates approximating the boundary, so you will have actually in the set the length of the boundary. So this is quite an important data to take into account. So when you know this set, actually you know the length of the boundary. Okay, so you can hear the shape, you can hear the length of the Okay, so and the same question, you ask omega modulo isometry, you associate the length spectrum, and question, is it injective? Okay, so we have these 2 questions. And it turns out that they are connected.
What are for surfaces and geodesics?
Yeah, so this problem exists exactly for surface, geodesic surfaces. So you namely you associate to a surface the length of its closed geodesics. Yes, exactly. And you can ask exactly the same question. You have way more results than with this one, actually. When we get
billiards are limits.
Yes, exactly. So it's broken geodesics. But yeah, the terminology is the same. Exactly. And actually for surfaces, when the surface is negatively curved and also some generalization, yes, this works well. But in that case, so we have broken geodesics and also this kind of things, and they are related. There is actually, maybe I will not give exactly what it is, but there is a bridge between the 2, and it was given by Anderson and Melrose. It's called the wave trace formula. It was in the 70s. Okay? And it tells that basically, if you take a domain, the Laplace spectrum determines the length spectrum, not exactly, but actually generically. In some sense, so if you take a domain which has specific properties but which are generic, then you can, knowing that, you can cover the length spectrum through this wave trace formula. So it appeared then, as a consequence, people tried to solve this when they tried to answer Kat's question. They tried to also answer it in that setting. Okay, so it makes sense somehow because you can understand the light spectrum through the Laplace spectrum. Okay, so okay.
But was there a way to go back?
If you manage to say that there is this length spectrum, this arrow is injective for this specific domain. Yeah, so you have no other pre-image, then yes, it would be. But it's not that. Yeah, it's immediate. Okay, it's like okay, the techniques are similar. There is this bridge, and it makes sense. But now it became independent. Yes. Yeah, that's it. Actually, yeah, I didn't mention that you have actually the case of Kat's question, if you observe these two examples, okay, it's beyond it's not in our context because I said already at the beginning I take convex domains which have smooth boundary, but this time to imagine these two domains, this one I refer to existing domains. They are obviously not isometric, but they have the same actually length and Laplace spectrum. This was proven by Corentin, Webb, and Wolpert. Okay, so it's actually one cannot hear the shape of drums, general drums, if the boundary is not convex. Okay.
So there the answer is positive.
Here,
Yeah.
for convex domain, we don't know. It's not known.
It's open.
No, it's not known. Let me just before I give the known results, I will just introduce one more thing. Namely, okay, I will now work with that. Okay, so when you take a domain to study other domains which have the same length spectrum, you can try to first look a little bit around that domain. Okay? You can try to massage it a little bit, to try to see if you perturb the domain, do I perturb the length spectrum? So this is the first question toward that question, to answer that question. And maybe you can let me restart. You study the formation of domains. You might put it. Let's have this below. You take an initial domain. Okay, let's call it omega 0. And you deform it continuously. Some topology, but still with convex domain. Let's try something. I try to remain convex. Yeah. Okay, so and this is omega. So you actually embed your initial domain in a family of domain, and we say CR smooth family with the tau in an interval, and CR smooth means when you parameterize the boundary, like arc length for example, then parameterization depends CR smoothly on then the question can reformulate it. Can I find such a deformation which preserves the length spectrum? So you say L omega tau is constant or not for omega. So is it possible? So in that case, we say that we call this deformation. So this is what we call a deformation. Okay, the deformation, you just move it, and when you have this condition that the length spectrum is preserved, then you call this deformation isospectral. So same spectrum. Okay, and the question is, if you find an isospectral, is it possible to find an isospectral deformation by domains which are not obtained by translation and rotation because it's a so the question is, is there isospectral deformation? Is there non-trivial isospectral deformation of omega 0? You fix a domain and you ask this question. And if no, we say that the domain is rigid.
So this still doesn't prove the injectivity, does it?
I don't
It's
know.
like local injectivity.
Exactly. This is local rigid. Exactly. Precisely.
I wonder, is it possible that the sequence of arbitrarily small deformations preserving the length spectrum, but there is no CR smooth family? Can such situation occur?
In a way that you ask if it is you can degenerate degeneracy in the smoothness. Yes, the only examples that are known are for some I can see C9, so it's exactly so. It may happen that when you I suppose yeah, and billiard when it's not C2 or not C3 is the limit actually when you want to study billiard, because when below C3 you may have some very weird orbits that appear. Yeah. So it's not known. What I'm going to study actually is also you can do some restriction on the boundaries. You can ask, for example, some symmetries. So if, like in this case, it seems that you have an axis of symmetry. That's when you deform it with a certain tau, you deform the domain and you preserve this axis of symmetry. And also you have another one. It seems like, so in this case, I have two axes of symmetry which are orthogonal to each other, and I will call deformation. I will say that they have a dihedral symmetry. If this is the case for all the domains of this kind of symmetries. Maybe the axis can move with the domains, but still two axes. Okay. Okay. Now, what do we know about these results? So you have many results. I will try to just mention the.
You could put more environments, not only periodic orbits, but some irrational rotation, non-convex.
Yes. What exactly?
Like in Coburg harmonización.
Yeah. So
It's richer, something richer than just this would be.
So yeah, billiards, they have always these Km curves.
Yeah.
Exactly. I will speak about them actually. They are
Some
always these
caustics.
caustics. Yes. It's connected to the existence of caustics, and we use actually these objects to prove some results of caustics because it gives really important information on physics. But as you, I'll be more specific. Yes. Well, actually, if I want to be more details, the objects that are actually contains information about the deformation are more periodic orbits because they are more unstable. And if you preserve something, studying periodic orbits often is really fruitful, even but more difficult because it's not yes, the literature. There was actually a first result by Osgood and Salman. So there was the first result by Osgood, Ellipse, and Salman in 88, and later a result by Vadim. So really later, so 2024. They showed that if you consider the set of domains with the same length, or so this they were doing for Laplace spectrum, and it was doing for length spectrum. The same set of the domains with the same length spectrum, then these sets are compact. Isospectral sets are compact, which is the first step. Compacity is close to finiteness. And then actually Salman later, in these years, he conjectured that they are isolated. Yes. So if you have the two, it's a conjecture. Okay? If you have the two, then you can sort of reduce isospectral sets to finite number of domains. But it's still a conjecture.
Do you consider only convex now?
Yeah, now it's convex, exactly. Later, then you that if you take an ellipse, okay, it's actually take an ellipse. This ellipse has two axes of symmetry. And if you deform it, precisely you deform this domain, then the deformation, they call it flat. Okay, so they look at symmetry deformation of the ellipse. So it's far from being it's far from being continuous only. So you look at symmetry deformation of ellipse, which preserve the Laplace spectrum, then the deformation is flat, namely the jet in tau here is zero for any order. It means that in the analytic category, in C omega, it works in the C omega category. If you deform an ellipse, preserving the Laplace spectrum with a C omega deformation, then it's trivial deformation. Okay. Yes. Then a bit
Is it
late.
still holding this symmetry dihedral?
Yes. Okay. And it's a deformation of the ellipse, the only ellipse. A bit later, it was actually extended by Kaloshin and Sorrentino. So I call the here. They work on completely different stuff, on existence of the invariant curve, but it has application to that, and they remove symmetry. Okay. And it was in 2016. And actually, okay, you have plenty of works. I cannot mention all of them, but maybe another recent one was by De Simone, Kaloshin, and Vadim. In 16 or so, 16, 17, they proved something like that. They proved that if you take a domain, which is not a disk, but almost a disk, and with an axis of symmetry, and you deform it, preserving this axis of symmetry and the length spectrum, then deformation is trivial. So this works also for almost circular domains. Okay. It's not deformation of a disk directly, it works also, but also for nearby domains. Okay. It looks a bit simple. You have a disk, so by continuity it works, but a bit more tricky than here. And actually, okay, it was extended. This was for length spectrum, and it was also extended for Laplace spectrum by, if I'm not wrong, by Guillemin and okay. And the result that I am going to prove can be related to that one, or can be understood in this context. So here it's close to a disk. Okay. What we prove is close to an ellipse. You take a domain close to an ellipse and you deform it.
Analytically?
No, finite. So it is here, it is C9, actually, C9 in deformation. And we deform it to something in some regularity, then if it preserves the length spectrum, the domain is okay, let's mention this thing. Okay, so let epsilon, let E be an ellipse of eccentricity. So how much it is, how far it is from a disk, the eccentricity, then there is epsilon, depending only on the eccentricity, positive, and an integer r depending only on e, positive, such that any domain omega C, which is, okay, we have this epsilon, it gives a neighborhood, so epsilon neighborhood in the CR topology, epsilon CR closed to ellipse. If you have a domain sufficiently close to your ellipse, then it is rigid under deformation. Then omega is rigid under deformation. Under symmetry deformation with symmetries, with dihedral symmetry. So we need to preserve the axis. So it's you have your domain, you have your ellipse, or a domain which is almost an ellipse. And it's omega 0, and if you deform it in a way that you preserve the two axes of symmetries, and you preserve the length spectrum, it implies that it is trivial. Okay, so this is the result that we
In other words, any deformation that obeys this has another length.
Yes, exactly. So if the deformation is not by translation or rotation, then you will change the next spectrum. We don't know what's happening when you have not symmetric deformation, or if you can reduce regularity, and we don't have explicit regularity. This regularity, you mentioned it, actually, it's related to Kn, the theory. It's given by Kn. So we don't have much control, precise control on this. Okay. These are the presentations. I will now go a little bit deeper into billiard dynamics and try to explain the ingredients. So if you don't have questions, I will continue. So the first, actually, question that we can ask is why the length? Why, when we look at billiard orbits, why do we consider the length of billiard orbits? And this is for a very specific reason. So when you take a billiard domain, strictly convex with a sufficiently smooth boundary, you can actually discretize the billiard. You have continuous trajectory, but you can look at discrete model. And when you take a point, point on the boundary, let's say you parameterize it by arc length, which you define infinitesimal length on the boundary, then you can parameterize it by arc length. And if you take a point, you can specify a number between starting from the tangent line and draw the ray of light which starts at S and makes a number 5 with the boundary. Okay? And this ray of light will hit the boundary at another point, S1, and be reflected with a certain angle, phi1. Okay? So we start with S5 and we arrive to S1 phi1, and this gives the billiard map. Actually, so you associate a couple S5, the next layer, S1 phi1. This would be the billiard map. And if you consider all the possible pairs of S phi, it defines the phase space M, which is actually almost which is actually a circle times if you consider phi between 0 and phi. Okay, and so this acts on the space. Yes, exactly. So this is called the phase space. And this phase space actually is a cylinder. If you put the S coordinates here and the phi coordinates here. So and the billiard map will act on this space. So if you take a point with the coordinate S and phi, you can associate another point. This one, phi 1. And the billiard map will send this point to that. Okay. The billiard map is actually an exact symplectic twist map. So, twist means that if you fix S, the point on the boundary, and you increase the angle phi, you see that the point S1 is also increasing. This is the twist. And it means that if you fix a vertical line here, so you fix S and you increase the angle, it will be sent on a inclined line by the billiard map. So this actually it's actually wrong. For the billiard map, you start here because they are fixed line, and then you this is the meaning of twist. Now, exact symplectic. So exact symplectic from exact symplectic geometry, you have it is exact symplectic. It has actually a generating map. In this case, this generating map is actually very simple, and it is the length, the distance between the 2 points. Let's call it L of S and S1. The distance. And being a generating map tells you that actually cosine, you can recover the dynamics using only these maps. Okay? It generates the map, it generates the billiard map. So cosine of phi is actually given by minus delta S of L, and cosine of phi 1 is actually delta S derivative S1 of L. Maybe we just change the, I'm not sure about the signs, but it's more or less something like that. So once you know L, you can recover the angles of the bounces. And so this is L, is the generating. Actually it's minus N. And so this relation actually tells you that when you find an orbit of the billiard map, then the points are actually critical points of that map. And this is why actually, because this map is actually very central in billiard theory, this is why the length tension is central. Let's do an example with the disk, which is really illuminating. At the same time, really simple, but so very illuminating. So let's draw this of radius 1. Okay, so we take a point on the boundary, and we will try to calculate the dynamics of the billiard map. So S is here. It bounds with we start with the number phi, and it bounds again at the point S1. Okay, actually, because we have a disk, here we have a triangle appears here you have the complementary angle, and so it means that here the angle is actually 2 phi. And since we have radius 1, so the length from S to S1 is actually 2 phi. So the dilemma can be written like that. S1 is S plus 2 phi, and phi 1 is okay, so very simple because there is a preserved quantity, and this you can see it as a rotation. Okay? And actually what is happening in the phase space when you fix an angle phi, all bounces will be on the same horizontal curve, which is preserved by the dilemma. And this works for any phi between 0 and pi. So you have a foliation by horizontal curve. Very, very simple. And actually it turns to be these invariant curves are connected with the existence of caustics that were mentioned before. Namely, you have concentric circles such that if you are tangent to it once and you bounce again, you will stay tangent to them. These two objects are connected. Yes. Okay. So what is the length now of this point? So L of S and S1. When we look at it, you can divide it in two. You apply a sinus, so you will have sinus phi that you multiply by 2. Okay, which is actually phi is actually 2 sinus S1 minus S over 2. So this is the length of this, so the generating map for this medium, and you can check up to the sign that we have. That was, sorry, is it? Yes, I think it corresponds to the size. Yes. That's everything what it is. Okay. There is a. Let's get interested into periodic coordinates. So if we look again at this, and we draw this satanic periodic coordinate. Okay, do 2 turns and 5 bounces. Okay. What is the angle phi in that case? So since you do 2 turns, okay. So if you multiply 2 phi by q, you will have 2 pi times p. Okay. Let's imagine that we do, instead of 2 turns, we do p turns, and q bounces you do instead of 5 you do q. Okay, just generalize. Imagine it's not 5 but p number, and p. It turns out that actually they have to be prime or prime, and so phi has to be pi p over q. And this p over q is really important. It's what you call a rotation number. And so what we prove is that L is 2 sine pi over q. And the perimeter of the orbit you multiply by q. Okay. So it is actually 2q sine pi over q p I. Okay. And I'm doing all of this just to then you can construct actually the length spectrum when you vary p over q over any rational possible, then you get all possible orbits or all possible perimeters that you're interested in for the length spectrum. Yes, the example of the disk is okay. You can define now the average action, average which are minimal in some sense. They minimize the action generated by L. And you can look at the average perimeter. So it's actually defined when in infinity you look at the average action. So we look at the sum over all possible distances, and then we average it with the number of bounds that we do. And we take the limit. Actually, when you have periodic orbit, it corresponds actually to perimeter. So you have a minus because the projection is like this, divided by Q. So when you have a periodic orbit. So we have this average action. For the disk, we take the perimeter, we divide by Q. Since everything is kind of the same length everywhere, we recover that. So beta of the disk. Here Q, actually for omega, is this 2 sine of omega. So if you know a little bit of Mark length spectrum, when, for example, you have a manifold with a closed geodesics, you can associate a rotation number to this geodesics. And once you have a rotation number, you associate the length of the minimum, the one with minimum length. Here it's the same. You take rotation number, and you associate a sort of a perimeter of the minimal perimeter of the periodic orbit. But you have to average because sometimes you don't hit some periodic orbit, so when you do perimeter, it doesn't. Okay, and why am I defining this? It's because of property of beta linked to isospectral domain. It is actually very convenient. This is the property that if your domain, you have a deformation which preserves the length spectrum, in tau, actually you preserve this mark. Although you specify some orbits. It's quite strong. So if omega tau is isospectral, so same length spectrum for any tau, okay, then you preserve delta. They are the same for all the domains and for any omega. So this is important because we have two domains which are isospectral. We have domains which have the same length spectrum, and we have something more. We have this delta, and we will work with that. Actually, what we are going to do is give a meaning to derivative this quantity in omega, which, so if it is constant, it should be derivative 0. And can we give a meaning to that? And retrieve information from that quantity. And actually it is possible, what we show is that it is possible if omega is sufficiently irrational, is there a quantile? There is a good expression that we can use and so this is going to be the last part of the talk. Trying to see. So if it is 1:30, I still have 14 minutes.
14 minutes.
So if you want to, you need to go. Just tell me. Okay. Yes. Mather beta function. It's called actually Mather beta function. Beta. It can be built for any domain. For any domain, and you take a rotation number, you can define this Mather beta function, which in the case of rational numbers is minus the perimeter divided by the number of points. Okay, so this is well defined, and we have an explicit expression for the disk.
Is there an explicit expression for ellipses?
For ellipses, there is actually precise. Yeah. Okay. So I think we finished. No, but exactly. So the whole point of the talk is of the result is actually to give a meaning to that for general domain, and then show that for ellipses you can say something more. Actually, you can use it. And you
says caustics happen ellipses or hyperbolas.
Exactly. And you use this
There are
property.
precise formulas for
Exactly.
this. By Rafał Kołodziej, he was PhD student in the US.
He was PhD
He
student.
died already. This was no.
Jacobi, no?
Rafał Kołodziej. He just wrote formulas.
I know formulas from
Maybe they were known,
I see.
but this
You read
is
this now?
elegant.
Yeah, okay. You have to write in the name because they are interesting.
Student of Żołądek.
Okay. Yes. So we'll give a meaning to that, provided that omega is actually Diophantine. And the reason is that when omega is Diophantine, you have some stability of these invariant curves. Okay, so in the case of the disk, we have a foliation of the space by invariant curves, very trivial ones because they are horizontal. For general domains, you still have invariant curves. They exist even if you're not perturbation of the disk. Just any domain, you have invariant curves. Not a foliation, but and they are curves. This is the game theory that you were mentioning.
So this second R has a properties like omega being, for instance, Bruno number.
Oh yeah, if you specify a weaker condition on omega. No, I think it's a strong condition.
So we get the Diophantine.
Yeah. There is actually a very famous paper of Lazukin which proved KM's theory for billiards, and he proved it with a specific set of numbers which are the strong.
There are Hermann conditions in various situations for just the mass of the circle.
Yes.
Between Bruno and Diophantine.
Yes. Yeah. It appears we don't need to go too much into. We don't need to merge these numbers. Maybe for general domains we need to study different numbers, but here it was sufficient. So this is a result due to, as I mentioned, Lazukin in the 70s,
Maybe Yokosuka.
which is the KM part, the KM theory applied to billiard. Lazukin showed that if you have a billiard with its base space, okay, so every are the ones considered by Laplacian actually. Which is interesting is that 0 actually is a density point of that set. So you have accumulation of invariant curves, and he said that for any omega in that set, you have an invariant curve, provided that omega is sufficiently small. So does it mean? Let me maybe briefly mention the theorem. Take any strictly convex omega, so we are in the convex, sufficiently smooth. In a sufficiently fine regularity that we can locate a lower bound, but we don't know exactly what it is. Any domain sufficiently smooth first has invariant curves. Of small omega e, meaning you have a lot of them. And also, these curves are smooth in a regularity that depends on the domain. Smooth at the same time in omega, in a weak distance. This set is sort of a counter set, but it makes sense to differentiate it, for example, at density points. So you can speak about differentiability of a set of invariant curves in omega, and also when you perturb the domain, KS theory will tell you that they are smooth in tau, the deformation parameter, when you perturb the domain. So you imagine you fix a domain, and now you perturb it. Okay. Then your free space here is changed. But if you fix a rotation number and you follow the curve, then it will move smoothly with the parameter. This is because of the stability condition given by this omega. And actually, okay, last notation, and then when you have such a curve, you can parameterize it such that the action of the map of this curve is conjugated to a rotation, to rotation number, with the rotation number omega. That's all. Let's define here the parameterization of that curve. Let's call it gamma of t, which is, if it's a point here, it will be x of t, and here phi of t. So gamma of t is the map, s of t, phi of t, in the phase space, parameterizing the curve, and such that t of gamma is the same as doing a translation by omega. So if you fix omega, so t acts like a rotation on the symmetry. So we have this gamma for a domain on which t is conjugated to a rotation of rotation number omega. When you move the domain, these curves are smooth in tau, and when you move to omega, they are smooth in omega. So these are important ingredients, and we can actually now compute derivatives of another beta function in the general domain, and this is actually the main ingredient of the proof that is new compared to the other results. This is what we found. Actually, if omega is a set, then let's say we start with the deformation. So we have, I draw it again, so this is here. When you have a deformation, you can compute the derivative of beta tau at omega. Okay, so let me rewrite. So beta omega depends on the domain, it's associated with the domain, and you differentiate it with respect to tau. And this has a nice formula. Maybe you take the integral from, let's say, gamma is from S1 to the phase S. From 0 to 1 of n of S t sinus phi t. Okay, where n is actually related to how the domains are displaced. And then you take a point on the initial domain. You take a point and you look at the distance between this point and the nearby points in the new domain. And this will be, let's call it distance S. Okay. And n will be actually the first variation. You can view it as the first variation of this distance in tau. Okay. So n gives you the variation. If you move your domain, how does it change with respect to the other domain when you look along the deformation?
I got lost with notation. So omega is given.
Yeah, omega is given.
And beta was what?
Beta was this matter beta function. This is the Mark length spectrum. So Mark length spectrum. And we look at how this Mark length spectrum varies with tau. Right? Even if it's
Omega is fixed.
yes, it is fixed, yes.
The curve moves, but omega is fixed.
Omega is fixed and only the deformation. And then you look at you have this formula that actually it depends on a lot of parameters. T is when you integrate along the parameterizing the curve. You integrate along the curve if you want. And omega is for this fixed rotation number. S is to this point on the curve, and phi is the corresponding number. So it's a sort of a curve integral along the curve here. It's not exactly curve integral, but and it relates the distance, the displacement of the two. And actually, if we manage to prove that this quantity is zero, if m of the displacement is zero, if the variation of the deformation is zero, then the deformation is triggered. This is a position. If m is zero in tau, okay, and in S also, in tau, and S, okay, then the deformation is triggered. And now maybe you see what we need to show is that if the domains are isospectral, okay, they have the same matter beta function. Hence, this derivative should be zero if this length spectrum is constant. Does it imply that n is zero? Does this equality imply that n is zero? In that case, we can say, okay, my deformation is triggered. So the question is this equality zero? And actually, for the ellipse, yes. But you can first view it as an injectivity property. Mention that. You can actually now, given the domain, if you fix omega, omega is a domain. You can associate a map, an operator, actually. You consider, let's call it E, I, omega, be the map which to head to function displacement. If this displacement is in the kernel, then it is 0, and the deformation is asymmetric. So the question is it injective, and how to prove that it is injective? So for a general domain, we don't know. For an ellipse, we can compute it exactly. And this is what I wanted to show. Okay, but here I take 10 more minutes, and then so it started to be technical, but maybe let's do something very practical, or very. So let's work with the ellipse. Case of the ellipse. So actually, a little bit like with the disk, when you look at an ellipse, you have the existence of caustics, and you mentioned these are hyperbolas or smaller ellipses, but confocal ones. So you have two foci, and you draw ellipses. We are interested only in the ellipses with the same foci, because we have our ellipse here, and we take a smaller ellipse. It has actually this one we say it has an eccentricity E, and you can actually define the eccentricity K of this smaller ellipse. And because of the property you were mentioning, actually any trajectory which is tangent once to the smaller ellipse will remain tangent after bouncing. Okay? So this is, you can do it as orthogonal property, a very specific one. But yes, so these are caustics. So smaller ellipses are caustics with eccentricity K. Yes. And of course then they correspond to invariant numbers, invariant rotation number, that we can write omega as a function of K. Each smaller ellipse has a rotation number. If you want to see in the phase space of the ellipse, you have invariant curve here, not foliating, but foliating the boundary, the lower and the of the cylinder, and in between there is actually, it's not so important for us, but you have this ice that appears corresponding to invariant manifold, stable and unstable manifold of some we're interested into this things. So for an ellipse, we will compute that formula with the formulas that you mentioned. I was told that, and I read a paper of Jacobi. So that's, yeah, maybe you have different proofs of this. Yes. So let's compute this quantity for an ellipse. Position. Omega is an ellipse. We can write this operator associated with n. It has quite a simple formula, I have to say. Go from 0 to 1 of n. There is a reparametrization x, I hide that a little bit. It's a reparametrization divided by 1 minus k squared, depending on omega. Okay? I say it's a family of sinus square of x. Okay, so let me maybe explain briefly. We have this integral which came from first derivatives of beta, and it gives a family of numbers, integral numbers, obtained from integral. Here, the dependency on omega depends on, is related to the smaller cost, okay? Which has an eccentricity k appearing here. Okay? So eccentricity squared times sine squared of x, the parameterization, and start an origin here out of this parameterization. Displacement in that direction will be the same as in that direction. So the n is even. And actually the fact that you have the axis here of symmetry tells you that it is also periodic with respect to that kind of transformation, and it turns out to be 1/2 periodic. So n is even, and 1/2 periodic. 1/2, I normalize everything by 1. So 1/1, it will be the same as here, the displacement, when you have 1. So the displacement will be the same as here, as at here, because of the fact that it is moving. Hence, the symmetries, they appear exactly here. And it is injective. Here, it's actually very easy to show that it is injective. Let's prove that. And then, or let's say it works well for nearby domains. So what we can do is look at this quantity and expand it when k is small for eccentricity. So we have an analytic function depending on k here. Okay? Forget that k is an eccentricity. When you move k, it works analytically. So if we fix n in L2, okay, and then you look at integral from 0 to 1 n of x as square root of 1 minus k squared sine square of x dx. And this you can expand using this formula, 1 minus 1 over x, 1 minus 1 over u is actually the sum of certain coefficients that are not 0 times u to certain power. So you do the Taylor expansion at 0 of this quantity. So this you can expand. You do sum over p positive of Cp k to the power 2p times the sine, you go from 0 to 1 of n of x sine 2p of x. Okay. You expand this as your u, this would be the u, and then you can put your integral to the permute integral and sum, and you have that formula. Now assume that this is 0 for any omega. Okay. We want to prove injective, so we take something in parallel. Then it means that if it is 0 for any omega, it will be 0 for any k. Because actually you associate omega to eccentricity, it's a different property. You can view it here actually. When you are, it's not so trivial, but for cases which are noticed, then this is actually omega associated k is actually a different prism. So this is true for any k. You see me coming, so it means that the Taylor coefficients of this expansion are 0. Hence, and this is not 0, so integral from of this quantity and x sine 2 pi x dx is 0 for any p. Okay, and
so you're talking about injectivity, but there you're checking only that it's not equal to 0.
Sorry? Yeah, so if you take n, sorry, the question was when?
So you're checking injectivity, right?
Yes.
But here you're checking only that it's not equal to 0.
You speak about the n for which is in the kernel. I take an n which is in the kernel.
This is a linear operator.
Ah, I see. Okay. Understood.
Yeah.
Okay.
Yeah, this is linear operator. Yeah, that's the exactly. Yeah, I understand your question. We could have, in generality, injectivity is if they are equal, if two ends give the same image, then it implies that the ends are the same, but it's linear, so you need to take something different. Exactly. That's the key point, is a linear operator. Okay, so it is injective for the ellipse. So the deformation of the ellipse are isospectral deformation of the ellipse with these symmetries are trivial. What about nearby domains? For nearby domains, injectivity, when you perturb an injective operator, it's not necessary that it is also injective. So for this, we use some finiteness that comes from another paper. Okay, so I will sketch it. Okay, so this is a paper that I mentioned by Decimoy, Kaloshin, and Vai. They hit these results close to it. They proved actually for any domain that if you have a deformation which preserves the length spectrum, you have a finite, you are in L2. Okay, we are in L2, we look at the space of deformation, namely the deformation map, the way the domains are displaced. They show that there is a plane, finite dimension 1, dimension of, let's call it P, dimension of P is finite dimensional, okay, such that if you have a isospectral deformation, it is in this set. So, contains the ends such that L omega tau is constant. So if you have isospectral deformation, in some sense, they are finite dimensional. So it's only a finite number of possibilities. And this plane is actually continuous. So if you move the domain, if I'm away from the ellipse, I keep finite dimensionality, but still not enough to conclude that it's zero. So we use that to show that actually there is a transverse hyperplane. Or let's draw a line. This is our hyperplane. So this is F KS. This is what we showed, that the deformation are here, and they intersect transversally for the ellipse. For the ellipse, you have a transverse intersection, and when you move your domain apart from the ellipse, you keep transversality because of this continuity. So there is transversality property that is something stable. So if you move a little bit the domain, you keep zero intersection, zero kernel. Everything works well because of this property. I think I should stop here, but if you want more details, I will be happy to answer questions. Thank you.
It's time for questions.
So, is there any chance you know how far from an ellipse you can go? Or I can illustrate this more precisely. So, because I can assume that if you are given an ellipse, you can just say something. But how does this depend on the ellipse? So, is there some kind of a uniform bound, which I doubt, but still,
This is an excellent question. So, so far for the ellipse, we cannot bound for any. It's not a neighborhood that depends uniformly on the ellipse. Also, the regularity doesn't depend uniformly on the ellipse, because if you look at family of ellipse, when you move eccentricity, the ellipse tends to collapse to a segment. So this k will tend to 0 actually, uniformly in oblique. When you have a disk, this function is actually not injected. It's actually just the average of them. So for that, it doesn't work at all. So when you look at the extremes, either you're close to disk or you tend to degenerate, then the neighborhood is kind of smaller. And also you need also make more regularities. When you want to get far from a fixed ellipse, no, I don't have it's a neighborhood which is given by k and theory. So this neighborhood depends on some implicit parameters. I don't have estimates. The question is, can we achieve the same results? Namely, and I put it in blue, ellipses are total, namely that this family, you can view this actually as a scalar product n with a certain density. This square root. It's a density depending on the medium. And the fact that it is injective tells you that this family is dense in L2. The question is, do you have other domains other than the ellipse for which this is true? And we don't know, and this is an important question. And so if we go far from the ellipse, does it still remain true? This is something not stable. And also, yeah, for general domains. So it's a really good question.
More questions? I have a question. This last bit of the argument with transversality, does it still require the symmetry of the...
Yes. Yes, it is, because for the ellipse we have transversality. We start at the ellipse, for which we have transversality, but transversality in this symmetrical two, function which are symmetric. So we need to keep it, definitely, because if you make the space a bit larger, it's not clear you have transversality. And how to pass to non-symmetric domains? It's not clear. Actually, I mentioned that the recent results where they remove symmetry from the ellipse is quite an exception. Like, probably the only result that managed to remove symmetries from this kind of rigidity result. And it's really surprising, actually, that so far the only generic result for not only ellipses or disks, they need symmetries. So the question which is open is, can you find deformation which is not symmetric, but preserving the symmetries? Is it possible? But preserving the length spectrum. Yes. And we don't know. Maybe you have counterexamples there.
Maybe there are some questions online.